We now move on to the next section, position, momentum, and translation. Okay, we'll start with continuous spectra. The observables that we considered so far have all been assumed to exhibit discrete eigenvalue spectra. So we did not mention this specifically, but all these eigenvalues that we talked about so far are discrete. Okay, for example, if you talked about the eigenvalue for the spin, z component of spin, it has just two eigenvalues, minus h bar by 2 or plus h bar by 2. There are no values in between. There are no values other than this. Okay. But if you take the z component of momentum, all right, if you take the z component of momentum, it can take any value between minus infinity to infinity. Okay. If there are no other constraints, the momentum can take values between minus infinity to plus infinity. All right, which means that when you make a measurement of the momentum, it will be a real number. So any real number could be a possible momentum for a possible value for measured momentum in the corresponding units, all right, in the appropriate units. Same is the case with position. Okay, if you take a particular component of position, right, x, y, or z, each of them can take values between minus infinity to infinity. All right, and again between any two possible points. All right, if you take any two possible points, there are again an infinite number of possible points in between. Even if you take any 2 points, however close they are, there will still be an infinite number of possible positions in between. Okay, so it's like saying that between any two real numbers, there are an infinite number of real numbers. All right. So the rigorous mathematics of a vector space is rather complicated. We don't go into the rigorous mathematics. Okay, but the things that make there are things that make it really complicated, right? For example, the dimensionality of such a space is infinite. Okay, here we talked about a two-dimensional space, and now we are trying to talk about an infinite dimensional space, right? And eigenvalue, the eigenvalue spectrum, right? There are, and what do you say, there are a continuous infinity of eigenvalues, right? There are a continuous infinity of eigenvalues. So all these things make the treatment rather complicated, but there are rigorous mathematical formulations. We don't discuss the rigorous mathematical formalism. What we will do is we'll start with the results that we already have, and then generalize it to the case of continuum eigenvalues, all right, or continuous eigenvalue spectra. So fortunately, many of the results we worked out for a finite dimensional vector space with discrete eigenvalues can immediately be generalized. All right, this generalization is possible. So in places where the straightforward generalizations do not work, we'll just mention. We start with the analog of an eigenvalue equation. In the discrete case, we had the eigenvalue equation A acting on ket A prime is equal to A prime multiplied by ket A prime. Okay. This is an operator. This is a vector, a ket. This is a real number. If you are talking about observables, this is a number. Okay, this is a real number, and this is again a ket. Right. In the case of continuous spectrum, we can simply write the corresponding eigenvalue equation. Right. We write it as psi acting on ket psi prime is equal to psi prime multiplied by ket psi prime. All right. So here, the psi sitting here is the operator without any primes. This is the operator with continuous eigenvalue spectrum. This ket psi prime is a vector. It's a ket, not a number. It's a ket. It's an abstract vector. This psi prime is the eigenvalue, which is a number, and this is again a vector. Okay. So psi is an operator. Psi prime is a number. The ket psi prime, or an eigenket of operator psi with eigenvalue psi prime. All right. Just as ket A prime is an eigenket of operator A with eigenvalue A prime. All right. So what is this ket psi prime? It's an eigenket of operator psi with eigenvalue psi prime. And again, we have used the same notation where we denote an eigenket with the corresponding eigenvalue. Okay? We are labeling the kets using eigenvalues. All right. In pursuing this analogy, we replace the Kronecker delta by Dirac's delta function. Okay, I hope you are already familiar with this Dirac delta function. All right. So wherever Kronecker delta symbol appears in the discrete case, in the cases that we discussed so far, we'll replace it by Dirac's delta function. All right, and then it works. Similarly, when you're talking about discrete eigenvalues or discrete eigenkets corresponding to discrete eigenvalues, you can just sum over all the possible eigenkets, right? Or you can sum over all the possible eigenvalues. Right? In this case, since the eigenvalues are continuous, you just cannot sum over all the possible eigenvalues. So what we'll do is that we'll integrate over all possible eigenvalues. All right. So the discrete sum over eigenvalues will be replaced by an integral over the continuous variable psi prime. All right. So for example, we have this expression in the discrete case, bracket a prime a double prime is delta a prime a double prime. This is the Kronecker delta, and this was called as the orthonormality relation. Okay. A corresponding relation in the continuous case can be written as bra psi prime ket psi double prime. Right? It's the same thing. It's inner product between two different kets, right? Or two kets in general, right? It could be the same ket. So we have got the inner product between two eigenkets of the psi operator, whatever that operator is. So the orthonormality relation can be written as bracket psi prime psi double prime is equal to delta psi prime minus psi double prime. This is the Dirac delta. This is the Dirac delta function, or simply the Dirac delta. Okay. So here you have Kronecker delta. Here we have Dirac delta. Also the completeness relation, the important completeness relation. In the discrete case, it's written as sum over a prime, ket a prime bra a prime equal to 1. In this case, instead of the summation, we'll have an integration over all the possible eigenvalues. So this is integral d psi prime, ket psi prime bar psi prime, okay, is equal to 1. Right? So this is quite easy to generalize in this way. Most results can be generalized in this manner. Let's look at a few more cases. So for example, we wrote ket alpha. We expanded ket alpha in the A basis. Right, and we call this as the expansion coefficients, and there is a sum over all the eigenvalues. All right. Correspondingly, here we'll have, instead of the summation, we'll have an integral over d psi prime. Right, so we can write integral d psi prime, ket psi prime bra psi prime, ket alpha. All right. You could also think of this as multiplying ket alpha by an identity operator, and instead of identity operator, we write ket alpha is equal to, insert an identity operator here, it's d psi prime, ket psi prime, bra psi prime, and then ket alpha, where this is the identity operator. All right. Now you can interpret this coefficients, these numbers, okay, bra psi prime ket alpha. These numbers can be thought of as the expansion coefficients in the same sense as here. Right? But since there are a continuous infinity of expansion coefficients, we will basically take it. So it's better to think of this as some function of psi prime. Corresponding to every psi prime, you get a complex number. So this gives you a complex number corresponding to every possible value of psi prime. And this is something that we are familiar with. Right? This is what we call a function. This is what we call a function of psi prime. So a function of psi prime is a rule that gives us a number corresponding to every psi prime. Right? Now, this is not just a real function. This could be a complex function. So maybe I'll write it as some psi of psi prime. This is a complex function that assigns a complex number to every value of psi prime. Okay. All right. Now, the normalization condition, right? The normalization condition, the idea that sum of the probabilities have to add up to 1 can be written as. So here there's a sum over a prime, and you are basically adding up all the probabilities. Okay. So modulus square of the probabilities amplitudes. So the modulus square of a probability amplitude is a probability. So if you add up all the probabilities, you should get 1. This is basically the normalization condition. And we get, correspondingly in the continuous case, we can write this as integral d psi prime. Instead of sum over a prime, we have got integral d psi prime. And the coefficients are written exactly in the same manner. Okay. Bracket of psi prime with alpha. Right? And then the modulus square, this has to be equal to 1. All right. Similarly, an inner product between two vectors. This is simply the inner product between two vectors. We can write this thing in the A basis like this, right? Sum over A prime. What I have done is I have just introduced an identity operator here. Sum over A prime. Ket A prime bra A prime is the identity operator. Okay. And we said we can write this as a multiplication of a column, a row matrix and a column matrix. Right? Now in the same manner, here we write this as bra beta ket alpha is equal to, instead of an identity in this form, we'll write an identity operator in this form, integral d psi prime ket psi prime Bragg psi prime. Okay, that's the identity operator that I'm going to include here. So this integral dx psi prime I pull out. I write it in this end, and then the rest of them I write together. Okay, so you'll have bra beta ket psi prime, that's this term, and then Bragg psi prime ket alpha. Okay, that's this term. All right. So this is how you write a scalar product in this representation, the inner product. All right. This is how you write the inner product in this particular representation. If you have studied wave mechanics, you might immediately recognize terms like this. All right. You might have seen terms like phi star of x, psi of x dx. You might have seen terms like this. All right. So these are scalar products of this form in a particular basis, right? Written out in a particular basis. Okay. And if we look at the matrix elements, we have got bar a double prime a get a prime, get a prime. These are the matrix elements of the observable A in the basis of its own eigenkets, and we know that it will be diagonal. So we write this as a prime delta a prime a double prime. All right. In the same way, in the continuous basis, this becomes, instead of this delta a prime a double prime, I will have a Dirac delta here. Here I have a Kronecker delta. Here I will have a Dirac delta. So this is the eigenvalue psi prime, right? This is the eigenvalue of operator psi, and eigenvalue psi prime delta psi double prime minus psi prime. Okay. Let's now talk about position eigenkets and position measurements. Position is an observable with a continuous spectrum of eigenvalues, right, or continuous eigenvalue spectrum. Now we have seen that a measurement in quantum mechanics is a filtering process. What does it do? A measurement of any observable changes the state into one of the eigenkets of that particular observable. This was what we saw in the discrete case, right? In the case of continuous spectrum, this thing is a little bit more complicated, but it's not very difficult. So we can extend this idea to measurements of observables exhibiting a continuous spectrum. Right? So let's talk about an example. Let's consider the position or coordinate operator in one dimension. So we are talking about the position of a system, right, or an electron in one dimension. So this is obviously an observable. The corresponding eigenkets, the position operator will denote simply as an x. Right? The corresponding eigenkets, the eigenkets of position operator will be denoted as ket x prime. So the eigenvalue equation can be written as x acting on ket x prime is the number x prime multiplied by ket x prime, the eigenvalue equation. Right? And again, just as in the previous case, this is a Hermitian operator. The eigenkets of a Hermitian operator form a complete set. So we can say that this set, ket x prime, forms a complete set. Here x prime is just a number with the dimension of length. For example, it could be something like 0.23 centimeter, or it could be something like 0.3 centimeter, or it could be like some 5 centimeter or 10 centimeter. This is just a number with the dimension of length, right? Where x is an operator, as we said. Now, since this is a complete set, since this forms a basis, these are eigenkets of a Hermitian operator called the position operator. This forms a complete set. So we can expand any ket like this. Ket alpha is equal to, we can write this as integral minus infinity to infinity. This is the range of positions available, minus infinity to infinity. Okay. Then I introduce an identity like this, dx prime, ket x prime, bra x prime. Then I write ket alpha here. So I can write ket alpha as an expansion, right, as an expansion over the position eigenkets. Okay, these are the expansion coefficients, which again can be thought of as a function of position. So you have got a function. We'll be dealing with a function that gives you a complex number corresponding to every possible position. Okay, again, you may be remembering wave function. This is exactly what the wave function that you have seen in wave mechanics does. Right? The wave function that you have seen in wave mechanics does exactly this. It gives you a complex number corresponding to every position. Okay. Of course, this is what we will later identify as the wave function. Okay. So first, let's consider a highly idealized selective measurement of the position observable. Okay. So suppose we place a tiny detector that clicks only when the particle is precisely at x prime and nowhere else. So our detector is so precise that it clicks only if the particle is at exactly a point, all right? Exactly a point. Right? So immediately after the detector clicks, according to our measurement theory, suppose the initial state was ket alpha, you could measure the position using a detector like this, an idealized detector, which clicks exactly when the particle is at x prime. Okay, so if I make a measurement of position, we know that the state will change to ket x prime, an eigenket of the position operator. Right? In other words, when the detector clicks, ket alpha abruptly jumps into ket x prime in much the same way as an arbitrary spin state jumps into sz plus or sz minus state when subjected to an SG apparatus of the sz type. Okay, this is again something that we saw. If you are starting with any ket alpha, you are making a measurement of sz, it will jump either to ket sz plus or to ket sz minus on a measurement. We don't know which. Before the measurement, we don't know to which state this is going to change, but it will change either to this or to this state. Okay. In the same way, if you make a highly idealized position measurement, it will change into the state will change into one of the eigenkets of the position operator. Okay. But in practice, the best the detector can do is to locate the particle within a narrow interval around x prime. So even when if we say that the position is at x prime, what we actually mean is that it's in an interval around x prime. If you're talking about one dimension, okay, the best we can do is to say that the particle is within these 2 points. Let's say x prime minus delta by 2 and x prime plus delta by 2. That's an interval of width delta. Right? A better detector may be able to narrow it down, but still we can talk only in terms of intervals. Right? Because even if you take any 2 points in space, there are still an infinite number of points between them. Now, when a count is registered in such a detector, so what does our detector do? It tells us in which interval the particle is. So the entire, if you're talking about one dimension, the entire x-axis can be divided up into small pieces, and the detector will tell me in which segment the particle is. Okay. Now, before the count is registered, the state can be expanded in the eigenkets of the position operator. So ket alpha is minus infinity to infinity, dx double prime, ket x double prime, bra x double prime, ket alpha. So this is basically the expansion of ket alpha in the position eigenkets. So we see that the limits of integration here are from minus infinity to plus infinity. Okay, which means that before I make the measurement, the particle is spread out over all the position eigenkets. It's spread out over all the position eigenkets, so it is in a superposition of all the position eigenkets. Now, what happens after a measurement? After a measurement, I can say clearly that, let's say that it's within this particular interval, right? We can say in which region the particle is. After the measurement, the state changes in such a way that it gets localized, gets in a way localized to an interval, right? It gets localized to an interval. So we can say that the state changes not to an eigenket of x prime, but still a superposition of all the position eigenkets, all right? Still a superposition of all the position eigenkets, but within a narrow range, right? So instead of this infinite range here, minus infinity to infinity, the particle changes its state, right, changes its state in such a way that it is now localized within a region x prime minus delta by 2 to x prime plus delta by 2. It's localized within this region. So the limits of integration are different here, right? But still it is slightly spread out over some of the position eigenkets. Right? It's still spread out. Here it's spread out over all the position eigenkets, the entire space. Here it has been narrowed down. Okay. So in the case of uh, continuous eigenvalue spectrum, we can talk about measurements in this form. We can say that ket alpha, which is spread out over all the eigenkets, changes, or it changes to another state, which is now what is it? It's not so spread out. All right, it's now within an interval. It corresponds to an interval x prime minus delta by 2 to x prime plus delta divided by 2. Okay. Now we need to calculate the probability. The question we are asking is, what's the probability that it changes to a particular interval? What's the probability that you'll measure the particle within a particular interval? All right. Now we cannot say the probability of measuring the particle at a particular point. Why? Because there are an infinite number of points. So generally, the probability is given by 1 divided by n, and if n tends to infinity, the probability goes to 0. Okay, so when there are an infinite number of points, you cannot say that, we cannot talk about the probability of measuring the particle at a particular point. There are an infinite number of points. Okay, but if you divide it up, divide the space up into intervals, then we can talk about the probability of finding the particle within an interval. Okay, all right. Now we see that even within this interval, right, even within this interval, there are some position states. So this is not one single eigenket of the position operator, but this is still a superposition of the eigenkets of the position operator. All right. Again, we can find the probability using the expansion coefficients. Let's see how. So suppose if it's a discrete case, suppose we are talking about a discrete case. Okay. Let's say that the state ket alpha is given by C1 ket A1 plus C2 ket A2 plus C3 ket A3. Okay, suppose the state is given here. You can ask the following question: what's the probability that the particle will be found in either ket A1 or ket A2 or ket A3? You're asking an OR question. What's the probability that it will be found in one of these states? Right. So for that you have to just add up the probabilities. It would be modulus of C1 square plus modulus of C2 square plus modulus of C3 square. Right. Remember here the question is not what's the probability of finding it in the state ket A1. The answer to that question is modulus C1 square. Right. The question I am asking is what's the probability that I find it in one of these states. Right. And then you have to add up all these probabilities. Okay. So in a slightly different notation I can write this as sum over, let's say, A prime, okay, within this region, right, within this state, sum over A prime, we can write bra A prime ket alpha and the modulus square. All right. So if I want to find it within these states, all right, I have to just add up over these states. I just have to add over these eigenvalues, if you like. All right, you have to add just over these eigenvalues. There could be other states, right? There could be other eigenkets like C for ket A3, etc. There could be other eigenkets, but the question I am asking is what's the probability that I'll find it in one of these three? Okay, and then I just have to add up the probabilities, right? In the same way, the question asked here is not about a specific position eigenstate, but we are asking about it being in a position eigenstate in this interval, right? In the position eigenstate in this interval. So within this interval, there are a large number of position eigenkets. All right. So if you want to find the probability that the particle is within this interval, you have to add all those probabilities up, just like we do here. All right. Okay. So here we are adding up all the probabilities. Correspondingly, we have to make an integration here. Right? So we have to integrate over all this region, x prime minus delta by 2 up to x prime plus delta by 2. Okay, and we know how to calculate these probabilities. So the probability the amplitudes for each ket or position eigenket is given like this. You have to take the modulus square of this, just as we do here. All right, and then you have to integrate. All right, then you have to integrate. Now this integration will give you the probability for finding the particle between x prime minus delta by 2 and x prime plus delta divided by 2. Okay, I hope this is clear. Now if you take this interval sufficiently narrow, imagine that you are making it so narrow, all right, that this thing does not change this thing considerably. Okay, this thing does not change considerably in the range. All right, so when you go from x prime minus delta by 2 to x prime plus delta divided by 2, this value, right, suppose this does not change considerably, it remains a constant, right? Or we have to take the interval so small that when you go from one point to the other in the interval, this function or this value does not change considerably. Okay, so let's say that we have a value bra x prime ket alpha. Let's say that we have a value bra x prime ket alpha, and modulus square of this, all right, modulus square of this, and we say that this does not change considerably within this interval. Okay, so throughout this interval, I can use the value bra x prime ket alpha modulus square. Right, throughout this interval, I can use the value bra x prime ket alpha modulus square. Alright, so assuming this does not change considerably within this interval, I can just pull this out and write it as the value corresponding to x prime. So I can write this as modulus x prime alpha, modulus bra x prime ket alpha square, modulus square of bra x prime ket alpha. Okay, and then I have got this integral x prime minus delta divided by 2 up to x prime plus delta divided by 2. This dx double prime is still there. Okay, now we integrate this. Now we can just integrate this. This is just an integration over, we just integrate dx double prime. It gives you x double prime. You apply the limits, so it becomes x prime plus delta by 2 minus x prime plus delta by 2. Okay, so you just integrate and substitute the limit. This becomes modulus bra x prime ket alpha square delta. Okay, so the probability of finding the particle within this interval can be written as bra x prime ket alpha square, modulus square of bra x prime ket alpha multiplied by the width of the interval, multiplied by the width of the interval. Okay, I think the calculation is here. Calculation is clear. The idea is that we are integrating over all the what is the probability amplitudes. Right, we are taking all the probability amplitudes, finding the modulus square and adding them. In this case, we are integrating them within this interval x prime minus delta by 2 up to x prime plus delta by 2. Then we make the assumption that this does not change considerably within this interval, so I can pull it out of the integral and give a specific value at x prime. Right, and then I integrate. I get modulus square of bra x prime ket alpha multiplied by delta. Okay, so this would be the probability for finding the particle in this particular interval. Okay, or in an interval around x prime, in an interval of let's say length delta around x prime. Okay, now assuming that bra x double prime ket alpha does not change appreciably within the narrow interval, the probability for the detector click is given by bra x prime ket alpha modulus square dx prime. Okay, so I use dx prime here to show that this interval is very small. It's infinitesimally small. Okay, so instead of using delta, I could make the interval smaller and smaller, and usually these small or infinitesimal intervals are written as differentials like this. Okay, dx prime. So here we have written dx prime for delta. This is analogous to the usual case of probability that we discussed in the case of discrete observables. Okay, this is analogous to bra a prime ket alpha modulus square for the probability of ket alpha to be thrown into ket a prime when a is measured. Okay. Now the probability of recording the particle somewhere between minus infinity and infinity, if you want to find the probability of recording the particle somewhere in space, minus infinity and infinity, if this is the interval you are talking about, you just integrate the thing or up from minus infinity up to plus infinity. Okay, so you can calculate the probability for finding the particle within any interval. All right, you could ask the question, what's the probability that it's somewhere in space? You can ask the question, what's the probability that the particle is somewhere in the entire space? Then you integrate from minus infinity up to plus infinity, this quantity. Right, and this quantity will be called the probability density. Probability density. Okay, it's probability per unit length, probability density. Okay, so multiplying with the length will give you the probability. All right, now again, as I said, if you are talking about the probability of finding the particle somewhere in space, this probability is 1, because if you are talking about a particle that exists, this particle has to be somewhere in the entire universe. It has to be somewhere in space. Okay, so this is the norm. This is what the normalization condition says. All right, so if it is normalized, this has to be equal to 1. Right, so if the state is normalized, this means that this integral is equal to 1. Okay, now if you have studied wave mechanics, you might have recognized by this time, right, this bra x prime ket alpha is nothing but the psi of x prime that you talked about when you studied wave mechanics. Right, over there we defined modulus psi of x square as the probability density, and this would be the probability. And if the state is normalized, that would mean that integral minus infinity to infinity modulus I of x prime square dx is equal to 1. Okay, if it is normalized. So this was the normalization condition. Alright. So basically wave mechanics is just quantum mechanics in the position basis or in the coordinate representation. Okay, so you can think of wave mechanics as quantum mechanics in the coordinate basis, all right, in a specific representation. Now we'll talk more about this later on. Okay. Now we can extend this to 3 dimensions. Right? The notion of a position eigenket can be extended to 3 dimensions. It is assumed in non-relativistic quantum mechanics that the position eigenkets ket x prime are complete. Okay, so this is ket x vector prime. So corresponding to every position, if you are talking about 3 dimensions, we have a position vector. Okay, so every position in 3-dimensional space can be represented by the corresponding position vector. Okay, so we'll denote these position eigenkets as ket x prime, x vector prime, which means that it has 3 components, because in order to pinpoint a position you need 3 coordinates. Okay, now the assumption is that these eigenkets form a complete set. The state ket for a particle with internal degrees of freedom, such as spin, ignored. So we are ignoring any internal degrees of freedom like spin, etc. All right. Then the wave function can be expanded. So the state ket alpha can be expanded in terms of ket x vector prime. Right. So then you can write as integral d cube x prime. Now this is a volume integral. All right. You are integrating it over the entire space. This is ket x vector prime, bra x vector prime, ket alpha. Now we just introduce the corresponding completeness relation here, assuming that these are this form a complete set, or this form a complete set, or this form a basis. Okay, alternatively, this actually means that you are just specifying x, y, and z. Right? You are specifying x, y, and z. Basically, you are specifying the eigenvalues of the 3 components of the position operator. So if you are looking at the position operator, it has 3 components, and you are specifying the eigenvalues of all these 3 components of position operator simultaneously. Okay, so x vector prime stands for x prime, y prime, and z prime. In other words, ket x vector prime is a simultaneous eigenkets of the observables x, y, and z. So these are the components. Right? These are the components of the position operator, the x component of position operator, y component of position operator, and z component of position operator. So this is basically a vector operator. Okay, you call it a vector operator, right? So ket x vector prime is this actually means that you are specifying the eigenvalues of all these 3 operators. Okay, now we know that if you want to be able to specify these 3 eigenvalues simultaneously, these operators have to be compatible. X, y, and z have to be compatible. Okay, which means that the commutators have to be equal to 0. Right? The commutators have to be equal to 0. So these are the eigenvalue equations. X acting on ket x vector prime is equal to x prime multiplied by ket x vector prime. Okay, this ket is an eigenket of operator x, okay, which is the x component of the position operator. Right, and this is the y operator. Y acting on ket x vector prime gives you the corresponding eigenvalue y prime multiplied by ket x vector prime. Z acting on ket x vector prime gives z prime multiplied by ket x vector prime. Okay, now to be able to consider such a simultaneous eigenket at all, we are implicitly assuming that the 3 components of the position vector can be measured simultaneously to arbitrary degrees of accuracy. We are assuming that there are such states. There are states which have common value, right, which have simultaneous eigenvalue for all 3 operators x, y, and z. In other words, we are talking about compatible observables. Okay. Compatible observables means we are talking about commuting observables. We must have commutator of xi with xj equal to 0. Okay. So here xi and xj means x1, x2, etc. Where x1 is another way of calling the x, x2 is y, and x3 is z. Okay, this may be more convenient notation. So we can write it like this: commutator of xi with xj is 0. whatever these are, x with x is 0, x with y, x with z, y with z, y with x, all these are 0. Okay. So we talked about observables with continuous eigenvalue spectrum. Continuous eigenvalue spectrum. Okay. As an example, we looked at the position operator and its eigenvalues. Alright. We talked about measurement of position, and we said that there's a small change in the language that we have to use in the case of continuous observables. Alright, but it's not very complicated. For example, we saw that we don't talk about the probability of finding the particle at a point. We only talk about the probability of finding the particle within a narrow interval around a point. Right? Suppose we are talking about the point x prime. We are talking about the probability of finding the particle within a narrow interval around the point x prime. And this probability is given by bra x prime ket alpha. If you are starting with ket alpha, this probability is given by bra x prime ket alpha modulus squared multiplied by the width of this interval, all right? So this quantity we call the probability density, okay? Now we saw that this is the usual wave function that you have. This thing is nothing but the wave function that you're familiar with from wave mechanics, okay? We also looked at the three-dimensional case, and we said that the state can be specified by giving simultaneous eigenvalues of all x, y, and z operators, all right? Okay, I think with that we'll conclude this session. Thank you.